Imagine this, my friend. Let's start with a bold assumption. Imagine you are standing on the grandest stage of your life. Maybe it's the Nobel Prize podium, maybe it's your company's IPO bell-ringing ceremony, or maybe you've finally secured that coveted tenured professorship. The spotlight is on you, the whole world is applauding you. You've made it. You've changed the world. Then, just as you get home, before the champagne is even popped, you receive an email. A competitor, one you've never respected, tells you in a polite but not so polite tone. Hey, congrats. By the way, that great discovery you won seems, from start to finish, to be wrong. How would you feel? Embarrassed? Ashamed? Or, guess what, you might be Enrico Fermi. Fermi. In the world of physics, this name is on the level of the Pope. That's not my title for him, it was literally his nickname. He became a professor at the University of Rome at 24, surrounded by a group of geniuses later known as the Rome Boys. This guy's aura was so strong that all of Italian physics revolved around him. However, unlike the real Pope, Fermi was poor. You see, ever since Galileo's glorious era, the Italian scientific community had been resting on its laurels. By the 1930s, their family fortune had visibly declined. If Fermi's team needed a piece of equipment, they had to build it themselves from the scrap heap. If they needed something to protect them from radiation, well, they had no protection. Their only safety measure was, after finishing an experiment, to collectively sprint from one end of the lab, 100-meter dash style, to the other end of the hallway. Why? Because they had just personally created a bunch of lethal chemical mixtures, and their only strategy was to outrun the radiation, hoping they wouldn't inhale a fatal dose. You might be wondering, what kind of divine experiment was worth this group of geniuses staging the Fast and the Furious in a hallway? My friend, they were trying to do something that, at the time, was no different from playing God. They were trying to create a new element. In our time, you pick up a periodic table, and boom, it's full. 118 elements, not one more, not one less, all neat and tidy. But in Fermi's time, that table looked a bit leaky. There were a few empty spots in the middle, like the one called technetium. But the biggest skylight was open at the bottom. The two entire rows we are now familiar with were almost completely blank. In that era, the elements that humanity could find in nature, in the air, in rocks, in groundwater, were all there were. Most of them, like the iron in your desk, are very stable, very content. But there was a small handful that were very restless. These radioactive guys were like a restless youth with 1,000,000 volts in his pocket but nowhere to spend it. They would randomly pew invisible bullets, like electrons, outwards to calm themselves down. These bullets can easily pass through your body. Marie Curie, Madame Curie, the radium she discovered, almost certainly murdered her. Her daughter, Irene, very likely died from polonium, another element her mother discovered. So, now you can probably understand why Fermi and his Rome boys would rather sprint down a hallway than stay 1 second longer. If running fast could extend their lives by even a few years, that sprint was totally worth it. Okay, here's the problem. Since nothing new could be dug up from nature, how could a dirt poor physicist create out of thin air a new element? In theory, it's actually dead simple. You only need to do one thing: add or subtract protons. You see, an element's ID card is determined entirely by how many protons are in its nucleus. Hydrogen has 1, so it's number 1. Helium has 2, so it's number 2. Lithium has 3. You just count your way up, all the way to the end of the known world at the time, number 92, uranium. So Fermi's logic was direct. I want to create element 93. I just need to stuff one more proton into the nucleus of number 92, uranium, and I'm done, right? But this is where the devil in the details comes in. The nucleus doesn't just have protons, it also has its good buddy, the neutron, which has no charge. Neutrons are like peacemakers or filler. Let's use carbon as an example. You and I are carbon-based life, right? Carbon always has 6 protons. But if it has 6 neutrons, it's carbon-12. It's very stable, calm and peaceful, unchanged for billions of years. But if it accidentally carries 2 extra neutrons, becoming 8 neutrons, 6 plus 8, it becomes carbon-14. This carbon-14 immediately gets anxious. It feels, too many neutrons, The energy is unbalanced, I'm uncomfortable. It urgently wants to correct this imbalance. So, it will, at a random moment, zap. Turn one of its extra neutrons into a proton, while simultaneously spitting out a high-energy electron to make change. This process, we call it beta decay. You see what happened? Is it still 6 protons? Nope. It's 7 protons now. Who is element 7? It's nitrogen. My friend, do you see? Just because it had 2 extra neutrons, this carbon atom became restless, and in the end, forced itself to become a completely, thoroughly new element. When Fermi saw this process, his eyes lit up. Isn't this just a cheat code? His idea was this: let's go to the end of the periodic table, find that heaviest, most bloated guy, element 92, uranium. Then, let's bombard the hell out of it. Bombard it with what? With neutrons. We're not expecting it to digest a proton. We're just going to feed it neutrons, feed it till it's stuffed. As long as we can feed it to the point of anxiety, force it to undergo beta decay, and make it turn a neutron into a proton. Then, element 92. Wouldn't it level up to 93? And if we're lucky, and we can make it level up twice in a row, don't we get 94 as well? It was a genius plan. A poor man's plan of creation. The Rome boys acted immediately. They sprinted down the hallway, placed a small piece of uranium in front of the neutron gun, and fired. But here, another interesting problem arose. How the fuck do you know if you've actually succeeded? After all, you don't know what element 93 looks like, and you don't know its chemical properties. It might decay and disappear in the blink of an eye. In this situation, Fermi and his team had to use the dumbest and also the most rigorous method, process of elimination. They had to prove what they hadn't created, to deduce what they had created. Thus, they began a long chemical investigation. They took the product of the bombardment and compared it with all known heavy elements adjacent to uranium, like 89, 88. All the way down to element 82, lead. Why did they stop at lead? Because in the physics understanding of the time, if a super heavy element was unstable, its most common way of death was a chain reaction called alpha decay. Simply put, the nucleus spits out 2 protons and 2 neutrons, which together are just a helium nucleus. This process is like hopscotch. Number 94 spits, becomes 92. 92 spits, becomes 90. It just keeps spitting its way down until it spits its way to a stable element. And that stable terminal station was usually lead. So Fermi's logic was clear: as long as my new stuff isn't lead or any of the relatives above lead, up to uranium, then it must be 93 or 94. They compared, and compared, and compared again. No match. The chemical properties of this new thing were completely different from all elements for lead. There was only one conclusion. Friends, we did it. Fermi and his Rome boys, in that dirt-poor lab, between sprints down the hallway, with homemade equipment. Humanity, for the first time, had created elements 93 and 94. This discovery made Fermi famous overnight. He became the pride and joy of Italy. Obviously, he had the first right to name these 2 new elements. At the time, he was under enormous political pressure. Some wanted him to name the element after the ancient Roman fasces, the origin of the word fascists. The person pushing for this name was Benito Mussolini. Yes, Fermi did not follow this suggestion. Let's pause here for a moment, catch our breath. This story is just warming up. If you love this kind of story, dancing on the scientific tightrope of a thought experiment, my friend, my creations depend on everyone's support. Give this video a like, subscribe, you absolutely won't regret it. Because next, the master we're about to meet, his blunder wasn't an accidental mistake. Okay, let's get back to Fermi. 4 years passed. The date is November 10th, 1938. 2 major events happened on Earth that day. First, in Germany, that night was known as Kristallnacht, the night of broken glass. Thousands of Jewish shops, synagogues, and homes were destroyed. Second, in Italy, Fermi's homeland, a series of anti-Jewish laws were introduced. Fermi's wife, Laura, was Jewish. Her passport was about to be revoked. So, when the phone rang at the Fermi house at 6 p.m. that day, informing Enrico Fermi that he had won the Nobel Prize in physics, his family didn't hesitate for a second. Fermi, his wife, and his children packed their bags and immediately left for Sweden to accept the award. After receiving the prize, they did not return to Italy. They headed west, settling in the United States. Just as he arrived in America, Fermi received a piece of news. News from Berlin, news that made his blood run cold. He was wrong. He, Enrico Fermi, Nobel laureate, the Pope of Italy, was wrong from start to finish. He had not created elements 93 and 94 at all. He had done something 10,000 times crazier. He had made an atom explode. Remember? The reason Fermi announced he had made new elements was because he had checked all the elements from 82 lead, 92 uranium, and found no match. It turns out, he should have looked at lighter elements. A group in Berlin, Otto Hahn and Lise Meitner, though Lise was already in exile, had repeated Fermi's experiment. But they saw what Fermi had missed. They saw krypton and barium. These two elements were too light, so light that they couldn't be the result of alpha decay. But if you add their proton numbers together, barium is 56, krypton is 36. 56 plus 36 equals 92. Who is element 92? Uranium. Fermi hadn't upgraded the atom. He had literally smashed a uranium atom in two. This process released a ridiculous amount of energy. Fermi, while trying to create element 93, had, completely by accident, discovered nuclear fission. This accidental discovery would fundamentally reshape the Second World War he had just fled. This accidental discovery would decide a global power struggle that lasted for half a century. And he, because of this beautiful mistake, received the Nobel Prize, and saved his entire family's life in the process. This is why I say Fermi is possibly the luckiest Nobel laureate of all time. Alright, friends, let's bring this thought experiment back to the beginning. Fermi's story throws us a soul-searching question. At the poker table of science, and even life, which situation is more fatal? Is it like Fermi, achieving greater success for the wrong reasons? He was wrong, but he unintentionally started the atomic age. Or is it pursuing a false success for intentionally wrong reasons? Fermi was unintentionally wrong. Half a century later, another person, in another element race, also made false claims. But that time, it wasn't an accident. It was completely intentional. This is a story about a man named Victor Ninov, and a story about the ultimate race on the periodic table. And to understand why that monstrous lie happened, why anyone would dare to fake it on the periodic table, we must first understand the island they were dying to land on. We have to draw a map first. You might be asking, hey, storyteller, those 93, 94, 92 you mentioned, aren't they just squares on the periodic table? What's there to talk about? My friend, you underestimate this table. The periodic table you and I are familiar with, that's just a table of contents. The real map is the one most people never see, the chart of nuclides. I have to show you this chart, the one I mentioned at the beginning. The x-axis is neutrons, the y-axis is protons. This is the key to everything. In my opinion, this isn't a physics chart at all. This is a topographical map of ambition, risk, and destiny. What you're seeing now is a vast continent. This continent is made up of those brown and red, high-standing pillars. Remember? These are the stable nuclides. We call this continent the path of stability. What is this? This is your and my comfort zone. Why? Because its half-life is billions of years. Do you get what that means? It's safe as hell. As long as you stay on this continent, don't do anything stupid, you can stably exist until retirement. This continent of stability starts at 1 hydrogen, and extends all the way up, perfectly balanced. But just like in our lives, you get halfway, around 20 calcium, and this balance starts to skew. You need more neutrons to maintain your stability. You go all the way up, and finally, you reach the end of this continent, number 82, lead. Friends, remember this name. Lead, the ultimate form of stability. Once you deviate from this continent, even by 1 step, you fall off. Fall off where? Into that blue, bottomless, raging sea. What is the raging sea? This is risk. On the continent of stability, your half-life is billions of years. And in the raging sea? When you fall into the orange shallows, your half-life is only a few minutes. When you fall into the blue deep water, your half-life is only a few seconds. And if you fall into the dark blue Mariana Trench, your half-life is milliseconds. Blink, you are here, you're gone. The entire universe may have only had that one you, atom. This is the graveyard of startups. But the scariest part of the raging sea isn't even that. The scariest part is that this sea, it has tides. Every part of this sea is against you. This radioactive tide is always trying to push you back to the same place. Push you back where? Back to the shore. Back to that continent of stability. To the south of the continent, the neutron-rich side, there is a tide, the one we talked about before, Fermi's cheat code, beta decay. You lose a neutron, but you gain a proton. See, this tide pushes upward. If you're smart enough, you can ride this tide, climbing step by step, to create new elements. But to the north of the continent, the neutron-poor side, there is another reverse tide. You lose a proton, you gain a neutron. This tide pulls downward. And at the end of the continent, in that great canyon, the heavy element region, there is the most spectacular tidal waterfall, alpha decay. Remember? Spitting out 2 protons, 2 neutrons, jumping 2 squares. Blink. 94 becomes 92. Blink. 92 becomes 90. This waterfall-like collapse will not stop until it reaches the stable lead. No matter where you start, no matter how hard you flail, you will eventually be pulled back to shore by the gravity of reality, the radioactive tide, pulled back to the main road of stable nuclides. Some people refuse to accept this. They want to go against the current. They want to climb up against the waterfall. They want to explore more of the ocean, and they suspect that, in the very middle of this raging sea, there might be another continent hidden. This is the myth that haunts the dreams of all physicists. The island of stability. Whose theory is this? Remember that female Nobel laureate we mentioned earlier? Maria Goeppert-Mayer. She proposed the magic numbers theory. Her theory is this. Friends, although the sea is dangerous, I've found a pattern. Protons and neutrons, they're like waltz dancers, they love to be in pairs. When their numbers are exactly 2, 8, 20, 50, 82, these magic numbers, they hold each other especially tight, especially stable. The end of the continent of stability, 82 lead, is a double magic number, both proton and neutron numbers are magic. This is why it's the terminal station of the continent. But Maria's theory gave one last crazy prediction. Although the continent of stability ends at 82, the magic numbers aren't finished. According to calculations, the next double magic continent should be at proton number 114, or 126, and neutron number 184. Right here. In the very middle of the raging sea. There is a magic island. My friend, do you get it now? This is El Dorado. This is Shangri-La. This is the myth. This is the ultimate dream of I want to change the world, super heavy element, and live a quiet life, super stable. This is the island of stability. It might exist. It should exist. But how do you get there? Look at where it is. It's surrounded by the deepest, bluest, shortest half-life death zone in the raging sea. You can't just walk there step by step from the continent of stability, lead. The moment you dip your toe in the water, you decay in milliseconds. The only way is to build a catapult. You need to take one end of the continent, say, calcium, and bombard the cliff at the other end, say, plutonium, and then pray that you can launch a few atoms that land exactly on that magic island. This is the ultimate prize that the scam of the century was centered around. Now, you understand the map. You understand the allure of this holy grail. Enrico Fermi, he accidentally fell into the shallows and blew up a new harbor, nuclear fission. He was too busy, he had to go to Chicago to build reactors, so he exited this treasure hunt. This chase was taken over by a brand new team. A dynasty that would rule this map for nearly half a century. And a captain who would, on this map, leave his own name. Friends, welcome the captain to the stage, Glenn Seaborg. This guy's story, from the very beginning, has an air of going with the flow. His father was a Swedish immigrant, last name Sjöberg. As soon as he arrived at Ellis Island, the immigration officer probably misheard, and with a stroke of the pen, decided their new family name should be Seborg. That name stuck. That customs officer never dreamed that his half-assed spelling would one day be printed on the periodic table. Glenn drifted since he was a child. When he was 11, his family moved from icy Michigan to sunny California. Little Glenn thought, since I'm in a new place, my name, Glenn, needs an upgrade too. So, he himself added an N to his name, Glenn, making it Glenn. Why? Because Glenn looks cool. A few years later, 24-year-old chemistry student Glenn was strolling through the Berkeley campus. Suddenly, someone from the radiation lab, Rad Lab, stopped him and asked, "Hey, buddy, are you in the chemistry department? Can you help us separate some chemical samples?" He was just the first chemist they grabbed on campus. Seaborg just wandered into the lab like that, and rose all the way up. Soon, World War II broke out. The boss of the lab, Edward McMillan, was drafted to work on radar and the Manhattan Project. Seaborg saw that the boss was gone, the throne was empty. He went and asked, can I take over? Become the new captain of the element hunt? The Berkeley dynasty begins. Remember? Before McMillan left, he had just confirmed element 93, neptunium. But he also left behind a recipe, a theoretical recipe for making element 94. Our dear Glenn got the first try. What was this recipe? Remember Fermi's beta decay? McMillan's theory was, if you add a neutron to uranium, 92, it will beta decay into 93. But what if you fire a deuteron, one proton and one neutron, at it? The proton will immediately make it jump to 93. Then, that extra neutron has a chance to trigger another beta decay, bumping it up one more time, to 94. Friends, this is like an extremely delicate game of Jenga. Yes, plutonium, just like that, arrived. It's safe to say, the discovery of plutonium was a huge fucking deal. It was quickly discovered to be even better bomb fuel than uranium. So, Seaborg and his team were immediately drafted to Chicago, to work with. Guess who? Oh, hey, our old friend, Enrico Fermi. These two titans were together. There, they spent several months artificially creating enough plutonium to level a city or two. The work was difficult and dangerous. Once, a lead brick fell and shattered a beaker, and it's rumored that 25% of the world's plutonium supply at the time was spilled onto a copy of the Chicago Tribune. But the Manhattan Project is another story. We care about Berkeley. By the end of the war, they had made enough plutonium. So Glenn and his team were finally free to think about other problems. Like, why stop at 94? The periodic table can't just end at such a weird number, right? They didn't even need to reinvent the wheel. Instead of starting from uranium, why don't we start from plutonium and just keep bombarding it with neutrons? Back to that Jenga analogy. You're trying to build a taller tower, but the base of your tower, those radioactive elements, is constantly disappearing. But, as long as your tower building speed is faster than its disappearing speed, maybe you can find a new element. Okay, friends, we need to speed up. Because the next dozen or so years are the mad chart-topping era of the Berkeley dynasty. This mind map looks like this. Element 93, discovered by Berkeley, McMillan. Element 94, discovered by Berkeley, Seaborg. Element 96, discovered by Berkeley members in Chicago, Seaborg. Element 95, also discovered by Berkeley members in Chicago, Seaborg. At this time, 2 atomic bombs were dropped on Hiroshima and Nagasaki. Element 97, discovered by Berkeley. They thought, it's finally our turn, right? So they named it Berkeleyum. Element 98, hey, guess what? Berkeley again. This time they named it Californium. After Berkeley continuously bagged for elements, even the New York Times couldn't stand it anymore, joking, hey, they should just call them Universicium, Ophium, Californium, Berkeleyum. Just then, the Nobel Committee finally recognized Berkeley's chart-topping achievement. Edward McMillan and Glenn Seaborg shared the Nobel Prize in Chemistry. You think it's over? Next up are 99 and 100. The discovery story of these two might sound extremely stupid, I swear I'm not making this up. The US, in the middle of the Pacific, detonated a hydrogen bomb. Then, they sent fighter jets to fly through the very top of the mushroom cloud to collect samples. Then, they frantically shipped these rapidly decaying things back to Los Alamos National Laboratory to analyze, to see if they accidentally made any new elements. Guess what? Yes. They fucking did. Since Berkeley also helped with the analysis, they shared the discovery credit for elements 99 and 100. They were named to commemorate the two greatest prophets of this field, Einstein, Einsteinium, and Fermi, Fermium. Both men had just passed away a few months prior. Soon, element 101 came along, discovered at Berkeley again. This is truly one of the most dominant winning streaks in scientific history. All other labs could only eat dust behind them, watching as the Berkeley dynasty added nearly half a row of new territory to the periodic table. As for Glenn Seaborg, he went with the flow again. He received an unexpected phone call from John F. Kennedy. He was appointed chairman of the Atomic Energy Commission. After creating the fuel for the first atomic bomb, Seaborg would spend the second half of his life dedicated to pushing treaties to limit the proliferation of nuclear weapons. Captain Seaborg came ashore. But the Berkeley dynasty continued. From 93 to 101, all theirs. But from this point on, the situation was no longer so clear. Controversy would play out on the geopolitical stage. Einstein famously said this about creating new elements. It's like shooting birds, in darkness, in a country where there are few birds. So true, man. The essence of element hunting is gambling. It's like a roulette game with the absolute worst odds. You spin once, the chances of hitting are low. But if you spin 5 million times at the table, your odds go from basically impossible to barely possible. And to spin a roulette wheel 5 million times, what do you need? Money. You need to keep that particle beam aimed at that target, continuously firing, for months. This is very, very expensive. A single day is tens of thousands of dollars. A few months is millions of dollars. And that's not even the deadliest part. The deadliest part is the target. Remember? The target at the beginning was uranium. The Earth is full of it, it's cheap. So making plutonium was easy. But the next level, your target, has to be plutonium. Further on, your target has to be curium, Einsteinium. With every upgrade, your target's half-life gets shorter and shorter, and the price skyrockets exponentially. 1 gram of uranium, 13 cents. 1 gram of Einsteinium, $27 million. Most casino regulars can't afford this kind of buy-in. Berkeley, in the richest state, California, of the richest country, USA, in the world, they had the most money, and the best equipment. So it's no wonder they had the advantage. But that's the charm of the casino, it's only a matter of time before another lab gets lucky. While the Americans were busy topping the charts and making bombs, the Soviets were awkwardly lagging behind. Of course, they were busy dying on the Eastern Front fighting the Germans. The Soviet nuclear program only got started thanks to a hothead, Georgy Flyorov. He was just a volunteer lieutenant on the Eastern Front. Before the war, he had been closely following the topic of nuclear fission. Until 1939, when all the Western academic journals suddenly went collectively silent. Flyorov thought, this isn't right. Nuclear fission is the hottest topic in decades, how come nobody is talking about it? He quickly connected the dots. Oh, my God. They are all building bombs. Flyorov went against all protocol and wrote directly to Stalin, basically demanding that the Soviet Union pour everything it had into nuclear technology. Amazingly, he wasn't shot for this, and instead became a key figure in the Soviet nuclear program. After the war, Flyorov changed his focus. He didn't want to build bombs. He wanted to hunt elements. He founded the JINR, Joint Institute for Nuclear Research, in a small Russian town called Dubna. Soon, element hunting went from a Berkeley solo act to USA versus USSR. Science, being used as a tool for Cold War proxy battles between hostile superpowers. From then on, almost every new element on our map would cause fierce controversy. This was the Transfermium Wars. This is how the battle went. First, a small lab in Sweden claimed they found element 102. Berkeley, USA, said, no, you didn't. Your equipment is cheap and crappy. Dubna, USSR, said, I agree with the Americans. Then the two of them teamed up to bully Sweden until no one believed Sweden really found anything. Then, Berkeley did the experiment themselves, and accidentally caused a radioactive dust leak, and the lab was evacuated. Then, Dubna, USSR, suddenly intervened with better results and claimed element 102 was theirs. Then, Dubna in one breath claimed to have discovered 104, 103, and then 105. The Americans, all they could do was desperately nitpick their data, saying, "Your methodology is wrong." This was the core of this war. The two sides had a fundamental disagreement on how to count a win. Dubna, USSR, preferred spontaneous fission. Their detectors were cheaper. They just listened for a pop. As long as the nucleus snapped in two, they'd say, "See, something." Berkeley, USA, said, "This method is unreliable. You don't even know what the fuck something split in two." The Americans preferred to track the alpha decay chain, that hopscotch. They wanted to see a complete chain of evidence. Because of this methodological disagreement, the data from this period is a total mess. It's almost as if this brutal competitive structure would lead to sloppy work. I sure hope this doesn't come back to bite anyone. For now, element hunting stalled. The end of the continent was too far. The waves of the raging sea were too high. By the time you get to element 101, the half-life is less than an hour. You can't even transport the target from Lab A to Lab B. Every gamble you take, you might create only one atom. One single atom. Before a second atom can join it, it has already decayed and disappeared. This clearly wasn't the end of the periodic table, but element hunting was becoming too expensive and impractical to continue. At least, not without a breakthrough. And the breakthrough came from the most unlikely direction. While Berkeley and Dubna were mud wrestling, a third player entered the stage. GSI, Institute for Heavy Ion Research, in Darmstadt, West Germany. GSI had money. Thanks to the post-war economic miracle. They had new technology. They came up with a brilliant idea. Why do we have to use uranium or plutonium as targets? That stuff is expensive and dirty, radioactive. Why don't we use the end of the continent of stability, lead, as the target? And then, we don't fire small bullets like neutrons or helium. We fire medium-sized cannonballs. Like iron? Think about it, lead, 82, plus iron, 26, equals 108. This is cold fusion, shares a name with that famous pseudoscience, but this is real science. This recipe required brand new beam technology, and more sensitive detectors. The Soviets were out of money. The Americans, for the first time, were out of ideas. The Germans, in just 5 years, using this new recipe, consecutively discovered elements 107, 109, and 108, in that order. The three-way poker table was officially set: Berkeley, Dubna, GSI. By the end of the 1980s, the ownership of 9 elements, from 102 to 109, was a complete mess. IUPAC, International Union of Pure and Applied Chemistry, that UN of Chemistry, stepped in. They spent years smoothing things over, trying to find a compromise that satisfied everyone, but in the end, only reached a compromise that left everyone only slightly unhappy. Among these new names, for the first time, the name of a living scientist appeared. Element 106 was named Seaborgium. Named after Glenn Seaborg. The captain, on the sea he had sailed for most of his life, left a permanent mark. It was a fitting end. Because Seaborgium would be the last element discovered by the Berkeley dynasty. Seaborg passed away. The Soviet Union collapsed. Dubna was dirt poor. To survive, they partnered with the most unlikely ally. Livermore Laboratory in California. You heard me. Berkeley's strongest rival, Russia, just teamed up with their next-door neighbor in California, Livermore. And GSI, Germany, had just won 3 in a row. Morale was high. Now, look at the situation at the poker table. The Germans are the new champions. The Russo-American alliance, Dubna Livermore, is probing the coastline of the island of stability. They claim to have discovered element 114 in 1998. And Berkeley? The former dynasty, the Pope, the chart-topping god? It had been almost 20 years since their last element discovery. They were washed up. They were ignored. They were desperate. They desperately needed a miracle. They desperately needed a secret weapon. They desperately needed a savior. So, they orchestrated a coup. Victor Ninov finally enters the stage. In the field of physics, it's hard to find stars. But if the physics world really had rising stars, Victor Ninov was, without a doubt, the chosen one. He was born in Bulgaria in 1959. When he was young, his family immigrated to West Germany. The word eccentric isn't enough to describe Ninov. He often signed his emails, "You're crazy Bulgarian." He loved cycling, he played the violin. It's rumored he even survived an avalanche accident, sustaining serious injuries. His adventures weren't limited to the ground. He once sailed the Pacific in a 45-foot sailboat. Somehow, he even had time to be a pilot, flying a single-engine Aero Commander plane. However, all this charisma paled in comparison to his most brilliant performance art. He and a colleague vowed to visit every Italian restaurant in Darmstadt, always order spaghetti carbonara, and then rank them. Friends, I have to comment, this is A-class performance art. I profoundly admire him. A Bulgarian, in Germany, in every restaurant, ranking Italian pasta. The logic is flawless. But Ninov wasn't just fun and games. He was the indispensable brain of the GSI lab. In 1988, GSI needed to upgrade their old computers. Ninov led this effort. He was the team's go-to computer technology expert. He even wrote a custom software package himself, named GOOSY. What is GOSY? My friend, this was his secret weapon. It was a one-of-a-kind, state-of-the-art software for analyzing the decay chains of radioactive samples. Before this, physicists had to manually look for peaks in analog signals, like looking for evidence in an EKG. GOSY brought element hunting into the digital age. Ninov, in his already niche field, found an even nicher specialty for himself. He was the only one who really knew how GOSY worked. Over the past decade, he was able to add a pretty nice bullet point to his resume. Co-discoverer of elements 110, 111, and 112. So, do you understand now? When Berkeley, in 1996, at all costs, poached Ninov from GSI. This was a scandal. This was academic espionage. This was blatant poaching. The man who orchestrated this poaching was an octogenarian, Al Ghiorso. Ghiorso was the last surviving titan from Berkeley's glory days. In the 1940s, he was just a kid installing intercom systems at the Berkeley lab, and accidentally met Glenn Seaborg's secretary, who later became Seaborg's wife. Through this connection, he joined the Manhattan Project. After the war, he returned to Berkeley and became Seaborg's right-hand man. He was born for element hunting. In the 1940s, Ghiorso was said to be the world record holder for longest-distance amateur radio, ham radio. Illegally, he didn't have a license. When Berkeley's accelerator was on one side of campus, and the chemistry lab was a mile away up the hill, Ghiorso would jump into his VW Beetle at midnight and illegally speed up the Berkeley hills, just to get the sample to the detector before it decayed into nothing. Once, he almost hit a security guard. The guard pulled a gun on him. He didn't even acknowledge him. He just kept driving. Nearly half a century later, Ghiorso, this old-timer, held the world record for discovering the most elements. So, when Ghiorso called Victor Ninov a younger version of himself, you hire that guy. Ghiorso was so excited that he came out of semi-retirement for this. Berkeley had a rising star. They had a chance to return to the top. The dream team was assembled. Ken Gregorich, in charge of the equipment side. Victor Ninov, in charge of the analysis side. They just needed a recipe. The Russo-American Alliance, dubbed Livermore, had just claimed discovery of 114. IUPAC, that UN, wanted more data. Berkeley had to claim this element. But they couldn't use the Russian recipe, plutonium plus calcium, because they didn't have enough plutonium, and this is dark humor, using weapons-grade plutonium in a densely populated area like the San Francisco Bay Area, was illegal. Yes, they could make it in Chicago, but they couldn't use it in Berkeley. Just then, another newcomer to the team, a visiting scholar from Poland, Robert Smolenczuk, proposed a crazy idea. He meant, "Friends, open your minds. Why do we have to go in order? Why are we fighting for 114? We should skip elements 113 to 117. Our target is 118. His plan was simple: bombard a lead 208 target with krypton 86. 36, krypton's protons, plus 82, lead's protons, equals 118. The advantage of this recipe: both of these ingredients are easy to get, and not radioactive. Conventional wisdom held that this recipe was too good to be true. The probability of this reaction was considered next to impossible. Remember the roulette analogy? We're going to use technical terms now. Physicists quantify this probability with a delightfully stupid unit: the barn. The word comes from the saying, "couldn't hit the broad side of a barn." One barn is considered a ludicrously large target. But when it comes to element hunting, this target keeps shrinking. Today, reactions are measured in picobarns. A picobarn is 1/trillionth of a barn. When you climb from element 102 to element 110, the odds of your gamble have worsened by almost 10 million times. And element 118? Most recipes predicted its cross-section, target size, was less than 1 picobarn. My friend, what does this mean? When you're down to the picobarn level, you run that multi-million-dollar beam for a week, you might produce one atom, and you might not even detect it. This is why Robert Smolenczuk's recipe was so controversial. Because, in his paper, he claimed his recipe could give you 670 picobarns. This isn't good. This is ludicrously good. This is a cheat code. If he was right, this would change the game. Not everyone on the Berkeley team was convinced. But the upside was, this recipe was low risk, high reward. And they needed to run a calibration test for the new machine, the BGS separator, anyway. So, they thought, why not use Robert's magic recipe? No one expected an immediate breakthrough. And yet, they basically got one. The experiment began on April 8, 1999. Most of the lab had left for the Easter holiday. The only exception was Victor Ninov. He stayed behind to analyze the results. 11 days later, the lab director, Darlene Hoffman, the Iron Lady who had missed discovering elements 99 and 100 due to sexism, got a call. Her first reaction was, this must be bad news. It's only been 11 days, what could it be? On the other end was Ken Gregorich. He assured her the situation was quite the opposite. A few minutes later, Gregorich and Victor Ninov arrived at her office. Ninov, in the early results, had found something incredible. He drew this diagram for his colleagues. Look. Blink. A particle comes in, perfect energy. Blink. It alpha decays, perfect energy. Blink. It decays again, perfect energy. A perfect alpha decay chain, starting at 118, becoming 116, then 114, and finally perfectly stopping at 110. Friends, what does this mean? If this was real, then the Berkeley team hadn't just discovered element 118. They had also discovered 116 and 114. And since IUPAC, that UN, was still arguing over the ownership of 114. This could be 2, or even 3. New elements for Berkeley. Their first in 25 years. Darlene Hoffman, this Iron Lady who had fought her whole life, her wish was about to be tripled. Ninov, like his colleagues, was in disbelief. He joked. Is Robert Smolenczuk talking to God now? They didn't announce it immediately. They took a few more weeks, ran another experiment. Bam! Another alpha decay chain was found. Bam! A third. With the 3 perfect decay chains they now had, the team deduced. 1, might be a fluke. 3, this must be legit. In June 1999, Hoffman and the semi-retired Ghiorso, 2 titans of element hunting, held a press conference. They announced their 2, 118 and 116, new elements. Berkeley was back. This career-defining paper was submitted to Physical Review Letters, PRL. The first author's name was prominently listed. Victor Ninov. He did it. This crazy Bulgarian, this plane-flying, postulating, GOSY-wielding Solaire. He, in 11 days, with an impossible magic recipe, had upended the entire periodic table. He became the king of physics. No doubt, the name Georgium was already in the works. But Ninov, clearly, had a bright future. He didn't get to hold this torch for long. GSI, the Germans, although they had lost their star, were eager to catch up to Berkeley. They immediately tried Robert's magic recipe. They did not see the alpha decay chains that Ninov had recorded. Nothing. Before the end of 1999, the team in France, and the team in Japan, also came up with nothing. This was weird. The Berkeley team, at this point, was also confused. They reran their own experiment in the spring of 2000. They also couldn't replicate the event. Friends, now *T, hit the fan. The Germans said, we saw nothing. The Japanese said, it's clean over here too. The French said, are you sure, you didn't see it wrong? But the most fatal blow was from Berkeley itself. They reran their own experiment in the spring of 2000. Still nothing. Nothing. Friends, you are now Darlene Hoffman, the head of Berkeley. How do you feel? This isn't bad luck. This isn't a statistical error. This is the ultimate nightmare of science, irreproducible. The sweat started pouring from the foreheads of the Berkeley top brass, the titans. This was no longer a scientific error. This smelled like a scandal. And so, the gears of internal investigation began to turn. They formed an independent working group, then an independent review committee, then a third, then a fourth. When the number of committees starts to exceed the number of elements you discovered, you know you're screwed. This last committee, its official name was the Formal Investigation Committee on Alleged Scientific Misconduct. See, even the name is so rigorous. Under the digging of these committees, the focus of the investigation had already shifted from, gosh, why can't we repeat the experiment, to, okay, we have to figure out who, and how, they faked all of this. Now, welcome to CSI, Berkeley. Remember? Ninov's ace in the hole was that custom software that only he knew how to use, GOSY. He was the sole data analyst. But my friends, the word soul in academia has an expiration date. 2 years passed. There's always some overachieving postdoc who will teach himself the damn software. A guy named Don Peterson, he was that overachiever. In May 2001, when Ninov again claimed that he had found another decay chain, the first one of 2001, in a new batch of data, Peterson finally made his move. He took the exact raw data file that Ninov claimed to have found the miracle in. On the same computer, using the same GOSY software. He pressed enter. The result he got was, element 118 does not exist. Friends, this is a fork in the road. Two top scientists, using the same software, analyzing the same data, came up with two completely opposite realities. One says, I saw God. The other says, there's nothing here. This wasn't a science problem anymore. This was fraud. The committee rushed in. They locked the servers. They needed to check the log files. They needed to figure out, how did Ninov do his magic trick? And what they found was so crude and so arrogant. Ninov's magic, in 3 steps. Step 1, the raw material. He first had GOSY analyze the raw data. What was in the raw data? Millions of random background noise events. GOSY faithfully recorded all of it. Step 2, the fake script. Then, Ninov manually, in text editor, fabricated a perfect script, those stunning alpha decay chains. He made up the energy values, the time values, all perfectly. Step 3, the switch. Finally, he used a command in the GOSY software that he himself had written. In the log files, this command left the criminal evidence of 2 dashes. What did this command do? Its function was to tell GOSY, hey, buddy, the next time you analyze, you don't need to actually analyze. You just take that fake script I wrote, file B, and copy-paste it into your analysis log, file A, and pretend that's the great discovery you just analyzed. Friends, this is like a magician, in plain sight, turning blank paper into cash. And Victor Ninov was that magician. He fooled everyone. He fooled Al Giorso, that beetle-driving old-timer. He fooled Darlene Hoffman, that lifelong fighter Iron Lady. He fooled Nobel Prize-level reviewers. He fooled physical review letters, PRL. He fooled the entire world. If the story ended here, this would already be a scandal of epic proportions. But the investigation committee was still digging. GSI, the Germans, Ninov's old bosses, their spines, also ran cold. The director of GSI, Sigurd Hoffman, he thought. Wait, this guy, when he was with US, did he? He went back and dug up the dusty old archives. Friends, buckle up. Sigurd found, Ninov had fucking done it. In Germany too. The exact same method. Sigurd recalled, back in the day, when Ninov was still at GSI, they were looking for element 112. The experiment had just started for 1 week, and Ninov excitedly ran in, saying, I found it. I found it. Sigurd, he's German, very rigorous, said, that's great. Bring me the printout of the raw data. Ninov froze for a second, and said, I'm busy. I can get to it. After lunch. You might have just discovered a new element, but you're too busy, perhaps, to go rank pasta? This is so fucking bizarre. Sigurd didn't think much of it at the time. Now, going back to check. In the original files, only radioactive background noise. But in the analysis report that Ninov turned in later that day, a perfect decay chain appeared out of thin air. Yes. I buried the lead again. Victor Ninov, what he tried to fake, wasn't 3 new elements, it was 5. 118, 116, 114. At Berkeley. And 112 and 110. At GSI. The only reason his 2 fakes in Germany got through was because his team, GSI, shortly after, actually found the real deal. GSI's real discovery covered up his, Ninov's, fake data. It's like a thief who stole a fake Ferrari model, only for his dad to actually buy him a real one the next day. He got away with it. But now, everything was exposed. The hammer fell fast. November 2001, Ninov was placed on administrative leave. May 2002, he was officially fired. The paper that had stunned the world, after dragging on for almost a full year, was finally retracted. Victor Ninov no longer works in physics. Okay. The detective story is over. But friends, that's not the point. How he did it doesn't matter. The point is why he did it. This is the truly creepy part of the story. This is where the story hits us. You see, in the same year, 2001, the physics world had another major fraud case, that Jan Hendrik Schön from Bell Labs. But Schön's motive was understandable. He did it to keep his job, for money, for fame. But Ninov? He didn't lack these things. He was already the star of GSI. He was already the co-discoverer of 3 elements. He was just poached by Berkeley, he was the golden boy, the top dog. He gained nothing, and lost everything. My friends, my theory is, Victor Ninov, he wasn't in it for the money, or the fame. He was a performance artist. He was too in love with that persona. He was too addicted to that script, the crazy Bulgarian, the plane-flying pasta connoisseur, the avalanche survivor, the computer genius who alone understood GOSY. He loved that all-powerful Victor Ninov. And when reality, that damned raw data, that uncooperative background noise, when reality couldn't match that genius script, he chose to modify reality. This is an ultimate, and most tragic form of imposter syndrome. He wasn't defrauding GSI. He wasn't defrauding Berkeley. He was defrauding himself. He needed this evidence to feed his genius persona. He needed this discovery to prove he was the younger version of himself that Al Giorso thought he was. He had sailed the Pacific, he had survived an avalanche. But he drowned at Berkeley. The terrifying part of this story is that all of us, to some extent, do this. When we post on social media, we Photoshop out the flaws, we add a filter, we carefully craft the caption. Aren't we also manually modifying the log files of our lives? Ninov's tragedy is just this humanity, magnified to the nuclear physics level. And the system. The cruel rules of element hunting, be first, or be nothing, this academic battle royale. This system encouraged this fraud. It rewarded the first person, not the most correct person. It was this system that selected Ninov. The real element 118, eventually, was found. Ironically, it was truly observed by the Russo-American Alliance, dubbed Livermore, in 2002, the year Ninov was fired. It was named Oganesson, after Yuri Oganesson, who is still the director of the Dubna lab. He is the second person after Glenn Seaborg to have an element named after him while still alive. And Al Ghiorso, that old-timer, passed away in 2010. He never got an element named after him. The seventh row of the periodic table ends at 118, Oganesson. My friends, this thought experiment should end here. We started with a lucky Nobel mistake, Fermi. We drew a topographical map of life, continent of stability versus raging sea. We witnessed the rise and fall of a dynasty, Berkeley. And finally, we dissected a genius's monstrous lie, Ninov. You might ask, we spend hundreds of millions of dollars, over decades, to chase these ghosts that disappear within milliseconds. What, exactly, is the point? Most of them, honestly, are useless. But utility was never the point. It's like when you were a kid, you tried to see how high you could stack your Lego tower, before it collapsed. We do this. Because why not? In that raging sea, in the midst of that island of stability, the biggest monster is not the unknown. It's ourselves. Alright, thank you for finishing this story. If you liked it, I hope you'll like, subscribe, and share. It's late, good night, my friends, and we'll see each other next time.